Picture yourself transported to a realm that challenges everything we know about planetary bodies. Io, Jupiter's extraordinary volcanic moon. In this astounding world, you wouldn't find the familiar stability of Earth beneath your feet. Instead, you'd experience a surface in constant turmoil, where the very ground writhes and transforms like a living entity. This is no mere geological curiosity. It's nature's most impressive display of volcanic fury in our entire solar system. As you stand on Io's surface, you would witness a truly otherworldly spectacle. Hundreds of active volcanoes punctuate the landscape, hurling molten rock high into the pitch-black sky, their eruptions painting fiery trails against the backdrop of Jupiter's imposing form. The ground itself pulsates with geological energy as new lava flows constantly reshape the terrain, creating and destroying features in a matter of hours or days. This relentless activity makes Io unique among all known celestial bodies, transforming it into a natural laboratory for understanding volcanic processes on a scale that dwarfs anything we see on Earth. What makes this spectacle even more remarkable is that it's happening on a moon roughly the size of our own moon, yet containing more active volcanoes than all other bodies in the solar system combined. The sheer intensity of Io's volcanism creates a hellish environment where temperatures can reach a scorching 2,000 degrees Celsius in its hottest regions. Massive lava lakes dot the surface, their molten contents reflecting the orange glow of Jupiter's distant light, while sulfurous compounds paint the ground in otherworldly yellows and reds. This fascinating moon stands as a testament to the raw power of gravitational forces in our solar system. Caught in an endless dance between Jupiter's overwhelming gravitational pull and the influence of its neighboring moons, Io experiences incredible tidal forces that literally knead its interior like cosmic hands working clay. This perpetual gravitational massage generates the heat that powers its extraordinary volcanic activity, making Io not just a curiosity, but a crucial piece in our understanding of planetary geology and the complex interactions between celestial bodies. As we contemplate this remarkable world, we're reminded that our solar system holds wonders that continue to challenge our imagination and expand our understanding of what's possible in the cosmos. Io's endless volcanic fury serves as both a window into the violent processes that shaped our own planet's early history, and a humbling reminder of the raw, untamed power that exists in the space around us. This is the story of a world that never rests, a moon that defies expectations, and a testament to the incredible diversity of planetary bodies in our cosmic neighborhood. The discovery of Io's volcanic nature stands as one of the most remarkable and unexpected findings in the history of space exploration. In March 1979, as Voyager 1 made its historic approach to the Jupiter system, the scientific community held relatively modest expectations about what they might find on Jupiter's innermost Galilean moon. Based on previous observations and the prevailing theories of the time, most scientists anticipated discovering yet another static, heavily cratered satellite similar to our own moon or many other moons throughout the solar system. The moment of discovery came through a combination of cutting-edge technology, keen observation, and perhaps a touch of serendipity. Linda Morabito, a navigational engineer at NASA's Jet Propulsion Laboratory, was performing her routine task of processing Voyager 1's images to precisely determine the positions of Jupiter's moons. While examining a photograph taken of Io's limb, the edge of its disk, she noticed something extraordinary. A mysterious plume extending about 100 kilometers into space above the moon's surface. This wasn't a photographic artifact or a data anomaly. It was something entirely unexpected and revolutionary, an active volcanic eruption occurring right before their eyes. The significance of this discovery cannot be overstated. For the first time in human history, scientists had confirmed the existence of active volcanism beyond Earth. This single observation shattered the long-held assumption that our planet was unique in its geological dynamism. The plume Morabito observed was later determined to be from a volcano that would be named Pele, after the Hawaiian goddess of fire. This eruption was just the first of many that would be documented on Io's surface. As Voyager 1 continued its observations, the spacecraft revealed an alien world that defied all expectations. Instead of the anticipated cratered surface, Io displayed a kaleidoscope of colors: yellows, reds, whites, and blacks, created by various sulfur compounds and silicate materials ejected from its many volcanoes. The absence of impact craters was particularly telling. Io's surface was so actively renewed by volcanic activity that any evidence of meteor impacts was quickly buried under fresh layers of volcanic deposits. This discovery marked a pivotal moment in our understanding of planetary geology. It demonstrated that significant geological activity could occur on relatively small worlds, challenging our assumptions about what drives planetary heating and geological processes. The traditional view that a body needed to be of substantial size to maintain internal heat was turned on its head. Io's volcanism, as scientists would later determine, was powered not by radioactive decay, as is largely the case on Earth, but by the immense tidal forces exerted by Jupiter and its neighboring moons. The revelation of Io's volcanic nature also opened new avenues in the search for potentially habitable worlds in our solar system. While Io itself is far too hostile for life as we know it, the discovery showed that smaller celestial bodies could maintain internal heat through tidal interactions, a concept that would later become crucial in understanding the potential for subsurface oceans on moons like Europa and Enceladus. Today, Linda Morabito's discovery is celebrated as one of the most significant findings of the Voyager mission, ranking alongside the detection of Neptune's Great Dark Spot and the discovery of active geysers on Triton. It serves as a reminder that in space exploration, we must always be prepared for the unexpected, for it is often in these moments of surprise that our greatest advances in understanding the cosmos occur. The extraordinary volcanic activity on Io is driven by one of the most fascinating mechanisms in our solar system, a complex interplay of gravitational forces that transforms this moon into a constantly churning furnace. At the heart of this phenomenon lies a remarkable orbital resonance between Io and its neighboring Galilean moons, Europa and Ganymede, combined with the overwhelming gravitational influence of Jupiter itself, creating what scientists call tidal heating. To understand this process, imagine Io as a rubber ball caught in an immense gravitational machine. As it orbits Jupiter every 1.77 Earth days, its path is affected by the gravitational pull of Europa and Ganymede. These three moons are locked in what astronomers call a Laplace resonance. For every 4 orbits Io makes around Jupiter, Europa completes 2 orbits and Ganymede completes 1. This precise mathematical relationship maintains a continuous gravitational interaction that prevents Io from settling into a perfectly circular orbit. Instead, Io's orbit becomes slightly elliptical, meaning its distance from Jupiter varies throughout each orbit. When Io moves closer to Jupiter, it experiences stronger gravitational pull. When it moves farther away, that pull weakens. This variation in gravitational force causes Io to be stretched when it's closer to Jupiter and compressed when it's farther away. The process repeats with each orbit, creating a powerful kneading effect within Io's interior. The numbers behind this process are staggering. The difference in Jupiter's gravitational pull between Io's closest and farthest points causes the moon's surface to rise and fall by as much as 100 meters. Imagine the entire surface of a world bulging up and down by the height of a 30-story building every orbital period. This continuous flexing generates an enormous amount of frictional heating within Io's interior, estimated to produce 100 times more heat than all of Earth's volcanoes combined. This tidal heating is so efficient that it maintains a significant portion of Io's interior in a molten state. Scientific models suggest that up to 50% of Io's mantle might be molten at any given time, creating a global layer of magma that may be up to 50 kilometers thick. This extensive magma ocean plays a crucial role in Io's volcanic activity, providing a readily available source of molten material that can be forced to the surface through numerous volcanic vents. The heat generated by tidal forces also explains the unique composition of Io's volcanoes. Unlike Earth's volcanoes, which primarily erupt silicate lavas, Io's eruptions often contain significant amounts of sulfur and sulfur dioxide. These materials, which give Io its characteristic yellow and red coloring, are heated to their melting points by the intense internal temperatures and are ejected alongside silicate materials in spectacular eruptions that can send plumes hundreds of kilometers into space. The efficiency of this heating mechanism is remarkable. While Earth's volcanic activity is primarily powered by radioactive decay in its core and leftover heat from its formation, Io's volcanic energy comes almost entirely from this gravitational dance. The Moon releases about 100,000 gigawatts of power through its volcanic activity, equivalent to thousands of nuclear power plants operating simultaneously. This powerful heating mechanism also explains why Io lacks the impact craters common on other moons. The surface is constantly being renewed by volcanic activity, with some areas being completely resurfaced in as little as a few months. Scientists estimate that Io's surface is completely renewed every few hundred to few thousand years, making it the most geologically active body in our solar system. The study of Io's tidal heating mechanism has profound implications beyond just understanding this one moon. Similar processes, though less intense, are thought to maintain subsurface oceans on Europa and Enceladus, making these moons potential harbors for extraterrestrial life. Thus, Io serves as a natural laboratory for understanding how gravitational forces can shape the geology and potential habitability of worlds throughout the universe. The volcanic features of Io stand as testament to nature's ability to create landscapes that seem to defy our earthbound imagination. While Earth's volcanoes are impressive in their own right, Io's volcanic features exist on a scale that transforms our understanding of what planetary geology can achieve. Perhaps most striking are Io's legendary lava lakes, which dwarf anything found on Earth. These vast pools of molten material can span hundreds of kilometers across, making them larger than many major metropolitan areas. The largest of these, Loki Patera, stretches over 200 kilometers in diameter, large enough to swallow several major cities. Unlike Earth's lava lakes, which are relatively stable, Io's lakes periodically overturn in their entirety, creating massive waves of molten rock that surge across their surfaces in a spectacular display of geological power. The volcanic plumes of Io represent another realm of extremes. While Earth's volcanic eruptions rarely exceed heights of 20 kilometers, Io's volcanic plumes soar to truly astronomical heights, often reaching 500 kilometers above the Moon's surface. These eruptions, propelled by the explosive combination of sulfur dioxide gas and silicate particles, create umbrella-shaped clouds that rain volcanic material back onto the surface in patterns that can span hundreds of kilometers. The most powerful of these eruptions can eject material at speeds exceeding 1,000 meters per second, creating spectacular displays visible from space. One of the most alien features of Io's landscape is its network of molten sulfur rivers. These extraordinary waterways flow across the surface, their brilliant yellow hue creating surreal patterns against the Moon's mottled terrain. Unlike Earth's water-based rivers, these sulfur streams maintain temperatures around 230 degrees Celsius, creating unique erosion patterns and deposit formations that have no parallel on our home planet. The sulfur rivers contribute to Io's distinctive color palette, painting broad swaths of the surface in vibrant yellows, reds, and blacks, depending on the temperature and composition of the material. The mountains of Io present yet another geological puzzle. Unlike Earth's mountains, which are primarily formed through the collision of tectonic plates, Io's towering peaks are born from massive crustal compression. As new volcanic material is constantly deposited on the surface, it creates tremendous pressure on the existing crust, forcing some sections to thrust upward. These mountains can reach heights surpassing Mount Everest, with some peaks soaring to 16 kilometers or more. What makes them even more remarkable is their isolation. They often stand as solitary giants on the plains of volcanic deposits, their steep cliffs telling stories of rapid uplift and constant geological change. The composition of these volcanic features adds another layer of otherworldliness to Io's landscape. While Earth's volcanoes primarily erupt silicate-based lavas, Io's eruptions include a complex mixture of silicates, sulfur, and sulfur dioxide. This creates a constantly changing surface where temperatures can vary from the extreme cold of space to over 1,500 degrees Celsius in active volcanic regions. The interaction between these different materials creates unique geological formations not seen anywhere else in our solar system. The speed at which these features change and evolve is equally remarkable. On Earth, geological changes typically occur over millions of years, but on Io, significant surface transformations can happen within weeks or even days. New lava flows can cover vast areas in hours, while volcanic plumes can deposit enough material to create new mountains in a matter of months. This rapid pace of geological activity means that Io's surface is constantly being renewed, making it one of the most dynamically changing worlds in our solar system. When we gaze across nearly 628 million kilometers of space to study Io's violent volcanic displays, we're doing much more than satisfying our scientific curiosity. The furious geological activity on Jupiter's volcanic moon serves as a remarkable laboratory for understanding our own planet's past and present, creating a bridge between cosmic exploration and practical Earth science. The study of Io offers us an unprecedented window into Earth's early history, particularly the Hadean Eon, when our planet was a molten world of constant volcanic activity. During this period, approximately 4.5 to 4 billion years ago, Earth's surface would have appeared remarkably similar to what we observe on Io today, a landscape dominated by active volcanism, with new crust constantly forming and being recycled. By studying Io's current volcanic processes, we gain crucial insights into how Earth's early crust formed, how volcanic activity influenced our planet's early atmosphere, and how such intense geological activity might have influenced the emergence of life on our world. The technological advances, driven by our need to study Io's extreme environment, have revolutionized how we monitor and understand volcanic activity on Earth. The development of sophisticated thermal imaging systems capable of detecting Io's volcanic hotspots through space has led to improved satellite-based volcanic monitoring systems here on Earth. These systems now provide early warnings of volcanic activity in remote areas, helping protect communities living near active volcanoes. The methods developed to track Io's volcanic plumes from a distance have also enhanced our ability to monitor volcanic ash clouds on Earth, crucial for aviation safety and emergency response planning. Furthermore, the study of Io's sulfur-rich volcanic emissions has significantly advanced our understanding of how volcanic gases interact with planetary atmospheres. This knowledge has proved invaluable in predicting how volcanic eruptions on Earth might affect our climate and air quality. The extreme conditions observed on Io have also pushed scientists to develop more robust computer models for volcanic behavior, leading to more accurate predictions of volcanic activity patterns on Earth. Perhaps most significantly, Io's ceaseless volcanic activity has helped scientists better understand the role of tidal heating in geological processes. While Earth's volcanic activity is primarily driven by internal radioactive decay and mantle convection, studying Io's tidally driven volcanism has provided new insights into how gravitational forces can influence geological activity. This understanding has proved crucial in analyzing how Earth's moon influences our planet's geology, and has even helped explain certain types of volcanic activity in Earth's history that previously puzzled geologists. The techniques developed to study Io's rapidly changing surface have also enhanced our ability to monitor active volcanoes on Earth in real time. Scientists have adapted the methods used to track Io's lava flows to better monitor similar activities on Earth, leading to more accurate predictions of lava flow paths during volcanic eruptions. This has direct applications in protecting communities living near active volcanoes, as demonstrated by improved evacuation planning and risk assessment protocols. The extreme nature of Io's volcanism has also pushed the boundaries of materials science. The need to design instruments capable of studying Io's intense volcanic environment has led to the development of more heat-resistant materials and more robust sensing equipment. These technological advances have found practical applications in Earth-based volcano monitoring equipment, making it possible to gather data from previously inaccessible volcanic environments on our own planet. Scientists studying Io have also gained valuable insights into how volcanic gases and particles interact with magnetic fields, as demonstrated by the interaction between Io's volcanic emissions and Jupiter's massive magnetosphere. This understanding has helped improve our models of how volcanic emissions on Earth interact with our planet's magnetic field, contributing to better space weather predictions and our understanding of how volcanic activity can affect Earth's electromagnetic environment. Through studying Io, we've also enhanced our understanding of how volcanic activity influences climate systems. While the scale and composition of Io's volcanism differ from Earth's, the principles governing how volcanic materials spread through an atmosphere and affect environmental conditions remain similar. This knowledge has proved invaluable in refining our models of how major volcanic eruptions might influence Earth's climate, helping us better prepare for future large-scale volcanic events on our own planet. Recent discoveries about Io's volcanic activity and its interaction with Jupiter's environment have revolutionized our understanding of this dynamic moon. The Juno spacecraft, which has been studying the Jupiter system since 2016, has provided unprecedented views and data about Io's volcanic behavior and its profound effects on the entire Jovian system. One of the most significant recent discoveries has been the detailed mapping of Io's volcanic hotspots. Juno's sophisticated infrared imaging capabilities have revealed that the moon's volcanic activity follows distinct patterns previously unknown to scientists. These observations have shown that some regions of Io experience periodic intensification of volcanic activity, suggesting a more organized internal heating system than previously thought. The spacecraft has identified over 400 active volcanoes, with some regions showing surprisingly regular eruption cycles. Perhaps the most groundbreaking discovery has been the detailed understanding of how Io's volcanic activity creates and maintains a massive plasma torus around Jupiter. This donut-shaped ring of charged particles, primarily composed of ionized sulfur and oxygen ejected from Io's volcanoes, encircles Jupiter at Io's orbital distance. Recent data has shown that this plasma torus is far more dynamic and complex than initially believed. The continuous volcanic outgassing from Io feeds this torus with approximately 1 ton of material every second, creating an electromagnetic interaction that significantly amplifies Jupiter's already powerful magnetic field. The Juno mission has also revealed surprising details about the temperature distribution across Io's surface. New thermal imaging has shown that some of Io's volcanic hotspots reach temperatures exceeding 2,000 degrees Celsius, significantly hotter than previously measured and even hotter than many volcanic features on Earth. These extreme temperatures suggest the presence of magma compositions that scientists hadn't expected to find on Io. Another fascinating discovery concerns the relationship between Io's volcanic activity and Jupiter's aurora. Recent observations have shown a direct connection between major volcanic eruptions on Io and intensifications in Jupiter's auroral displays. When Io's volcanoes are particularly active, the increased material in the plasma torus leads to more intense interactions with Jupiter's magnetosphere, creating spectacular auroral storms that can be observed by spacecraft and telescopes. The distribution and behavior of Io's mountains have also been revealed in new detail. Recent high-resolution imaging has shown that these mountains, some towering higher than Earth's Mount Everest, are not randomly distributed across the Moon's surface. Instead, they follow patterns that suggest a global system of stress in Io's crust, providing new insights into how the Moon's interior structure responds to intense tidal heating. Juno's observations have also led to the discovery of previously unknown types of volcanic features on Io. Scientists have identified what appear to be hybrid volcanic structures that combine characteristics of different types of volcanic vents seen on Earth. These features suggest that Io's unique combination of intense tidal heating and low gravity creates volcanic processes that don't exist anywhere else in the solar system. The interaction between Io's volcanic plumes and Jupiter's intense radiation environment has revealed another surprising phenomenon. Recent data shows that the volcanic material ejected from Io undergoes complex chemical transformations as it interacts with Jupiter's radiation belts, creating unique molecular species that then rain back onto Io's surface. This chemical factory helps explain the Moon's distinctive color patterns and surface composition. Perhaps most intriguingly, recent observations have shown evidence of possible subsurface magma chambers that are far larger than any known on Earth. These massive reservoirs of molten material appear to be connected through a complex network of channels, suggesting that Io's internal structure is even more complex than previously thought. This discovery has important implications for our understanding of how planetary bodies can maintain long-term volcanic activity. The latest data has also revealed new insights about the composition of Io's volcanic emissions. While sulfur dioxide has long been known to be a major component, recent spectroscopic analysis has identified a variety of other compounds, including sodium chloride and potassium salts, providing new clues about the composition of Io's interior and the chemical processes occurring beneath its surface. The future exploration of Io represents one of the most ambitious challenges in planetary science, offering tantalizing possibilities that could revolutionize our understanding of volcanic worlds. As space agencies and private companies develop increasingly sophisticated technologies, the prospect of studying this volcanic moon up close is moving from science fiction to potential reality. One of the most exciting possibilities on the horizon is the development of heat-resistant probes, specifically designed to survive Io's extreme environment. Engineers are currently working on materials and systems that could withstand temperatures exceeding 1,500 degrees Celsius, while protecting sensitive scientific instruments. Advanced ceramics, similar to those used in spacecraft heat shields but significantly more robust, are being developed. These materials, combined with active cooling systems and innovative thermal management solutions, could make surface exploration possible within the next few decades. The potential for surface mapping missions presents particularly intriguing opportunities. Future missions could deploy networks of small, hardened sensors across Io's surface, creating the first comprehensive real-time monitoring system of an extraterrestrial volcanic world. These sensors would need to be designed not only to withstand the extreme heat, but also to survive in an environment where the ground itself might become molten at any moment. Proposed designs include spherical probes that could roll to safety if threatened by approaching lava flows. High-altitude missions also hold great promise. Future spacecraft could deploy a network of temperature-resistant drones or balloons in Io's thin atmosphere, allowing for close-up studies of volcanic plumes and their composition. These aerial platforms could provide unprecedented views of eruptions in progress and help us understand the complex chemistry occurring within the plumes themselves. The development of subsurface imaging technology represents another frontier in future Io exploration. Scientists are working on techniques to peer beneath the moon's ever-changing surface, potentially revealing the network of magma chambers and channels that drive its volcanic activity. Ground-penetrating radar systems, designed to function in high-temperature environments, could map these underground structures and help us understand how Io maintains its intense volcanic activity. Sample return missions, while extremely challenging, represent perhaps the holy grail of future Io exploration. The ability to bring back material from Io's surface would allow scientists to conduct detailed analysis of volcanic rocks and minerals formed under conditions that cannot be replicated on Earth. Such samples could provide crucial insights into the early history of our own planet when it was similarly volcanic. The search for potential biosignatures, while not a primary focus of Io exploration, could yield surprising results. While Io's surface is incredibly hostile to life as we know it, studying how complex organic molecules behave under such extreme conditions could provide valuable insights into the limits of chemical complexity in the solar system. Some scientists speculate that Io's subsurface regions, where temperatures might be more moderate, could host unique chemical processes relevant to our understanding of life's origins. Technological developments in the field of radiation protection will be crucial for future Io missions. The Moon's location within Jupiter's intense radiation belts poses a significant challenge for electronic equipment. New advances in radiation-hardened electronics and shielding technologies will be essential for any long-term presence around Io. The potential for establishing a long-term monitoring station near Io is another exciting possibility. Such a station could provide continuous observation of volcanic activity and help us understand the Moon's volcanic cycles and patterns. This could be achieved through a network of small satellites in Io's orbit, designed to withstand both the radiation environment and the constant rain of volcanic debris. Future missions to Io could also help us understand fundamental questions about planetary formation and evolution. By studying how tidal forces continue to shape Io, we might gain insights into how similar processes influence the early solar system. This knowledge could be particularly valuable as we discover and study volcanic exoplanets around other stars. The economic potential of Io, while speculative, cannot be ignored when considering future exploration. The Moon's constant volcanic activity produces rare Earth elements and other valuable materials that could, in the very distant future, make it a target for resource utilization. While such activities are currently beyond our technological capabilities, understanding Io's resource potential could influence long-term exploration strategies. The challenges of exploring Io will drive innovation in numerous fields, from materials science to robotics. The technologies developed for Io missions could have applications in other extreme environments, both in space and on Earth, particularly in the study and exploitation of volcanic and high-temperature industrial environments. Our journey through the fascinating world of Io serves as a powerful reminder that our solar system is anything but a quiet, unchanging place. This small moon, with its endless volcanic fury, challenges our preconceptions about what's possible in our cosmic neighborhood and continues to surprise us with each new observation. Io stands as a testament to the dynamic nature of our solar system. Its constant volcanic eruptions, shifting surface features, and powerful interactions with Jupiter paint a picture of a place where change is the only constant. This perpetual transformation forces us to reconsider our understanding of planetary geology and the forces that shape worlds throughout the universe. What we observe on Io today, the towering volcanic plumes, vast lava lakes, and rivers of molten sulfur, represents just a snapshot of an eternal process of destruction and renewal. The significance of Io extends far beyond its role as Jupiter's volcanic moon. It serves as a natural laboratory for understanding fundamental processes that shape planetary bodies throughout the cosmos. The intense tidal heating that drives its volcanic activity provides insights into how gravitational forces can maintain geological activity even on relatively small worlds. This understanding has profound implications for our search for potentially habitable worlds beyond our solar system. The story of Io's discovery and continued exploration also reminds us of the importance of keeping an open mind in scientific endeavors. When Voyager 1 first revealed Io's volcanic nature, it shattered our expectations about what we might find in the outer solar system. This discovery stands as a crucial lesson that the universe often defies our assumptions, and some of the most important scientific discoveries come from being prepared to recognize the unexpected. Moreover, Io's study has practical implications for our understanding of Earth. By observing the extreme volcanic processes on this distant moon, we gain valuable insights into our own planet's volcanic systems and early history. The technologies developed to study Io's harsh environment have led to improvements in how we monitor and predict volcanic activity here on Earth, demonstrating how space exploration can yield practical benefits for life on our home planet. As we look to the future, Io continues to present both challenges and opportunities. The extreme conditions on its surface push the boundaries of our technological capabilities, driving innovation in materials, science, engineering, and spacecraft design. Each advance in our ability to study this fascinating world brings us closer to understanding not just Io, but the fundamental processes that shape planets and moons throughout the universe. Perhaps most importantly, Io reminds us that we live in a solar system filled with wonders waiting to be discovered. Every new mission, every observation, and every analysis brings fresh surprises and deepens our appreciation for the complexity and diversity of our cosmic neighborhood. The ongoing study of Io exemplifies the essence of scientific exploration, a never-ending journey of discovery that continues to expand our understanding of the universe and our place within it. In closing, while Io may seem like a distant alien world, its study connects us to some of the most fundamental questions in planetary science. How do worlds evolve? What forces shape the planets and moons around us? How can seemingly small bodies maintain such intense geological activity? As we continue to explore and study this remarkable moon, each answer we find leads to new questions, driving us forward in our quest to understand the cosmos. The legacy of Io's exploration will continue to influence our understanding of planetary science for generations to come. As we venture further into space and develop new technologies to study distant worlds, The lessons learned from this volcanic moon will guide us, reminding us that in our solar system and beyond, the most extraordinary discoveries often come from the most unexpected places.